Well, good morning, you guys. Here's part 2 to your notes today, and I thought I'd add a little bit more to it because I have a feeling that other stuff is probably somewhat of a review. And so let's ramp it up just a little bit. This next modeling with exponential and logistic functions, so we can take this exponential function to the next level. You know how we had a b to the x? Well, a and b are going to get a little more sophisticated, and we're probably going to stop using x a lot. But this model that you see in front of you, that p naught, that p sub 0, it's like peanut, that is your a, your initial value, your starting amount. And b, the base, the thing that's being raised to some power, is now 1 plus r. And the reason this is great, and then of course x, sometimes we use t. Time is probably the most commonly used form of exponential growth. We do it in terms of time. And then r inside there, that's where we put our percentage rate. So if I say, 5%, that's our rate of growth. Now we can really talk about it in terms of something more familiar, which is like, growing at 5% or decaying at 5%. Remember, we want to use the decimal form anytime we're doing calculations, mathematical calculations, in a rate of change, rate of growth, and a percent is involved, you better use the decimal, 0.05. So all that stuff is kind of summed up inside here. It says down here if r is less than 0, then we're talking about a decay. So basically, here's decay is growth as what you see in that model up there. It's p naught 1 plus r, so you get like 105 to the t if that were 5%. Now decay, so this is, should we label that growth, like that? Our decay is when we have that p naught and it's 1 minus r. You actually subtract away that rate. So if it's 5%, what that would produce is 95% inside there. So that's actually another indicator of growth and decay, is if you see after the p naught some kind of, let me give me a little tester here. What if I give you 0.85 to the t? Somebody says, hey, is that a growth or decay? Well, that number there, it's less than 1, so this is decay. It's some percentage got subtracted from 1, and somebody might say, well, okay, what's a decay, but at what rate? Well, then you'd have to say, how far is that from 1? That's 15%. Got it. There you go. So that would be a decay rate of 15%. Likewise, growth rate is the percentage difference from 1 on the upper side. All right, so we got San Jose. Tell whether the population model is exponential growth or decay, and then find the constant percentage rate of growth or decay. Kind of the same thing I was just saying. Well, let's just list through some things. In that San Jose, that number right there in the front, that's your initial amount, initial population. Detroit, there's your initial population, that first number. The rate of growth, that rate that we're looking for, is the difference from 1. So it's 0.0064 on the San Jose side. And it's the, oh my word, it's a blob on my page. Is that a blob on your page? Whatever number from, I think it's 0.9858, so I'm thinking 0.01, I don't know, I barely can read that. Hi, Graham. 4.2, something like that. The difference from 1, that's a decay, so Detroit decay, and San Jose growth. Now you guys kind of know the history on Detroit. When the markets crashed a few years back, the automobile industry was hit pretty badly, and Detroit's population was definitely hit the decline. I think even prior to that they were on a decline, and then it was ramped up. Oh yeah, Graham really wants to be noticed by you guys. Yeah, I think we should have some sweet potatoes. So I'll finish this up with you guys, and then I'm going to give Graham some sweet potatoes. Remember when I told you we gave him too many sweet potatoes and he turned orange? Well, it's okay. He really likes them, so we're going to go for it in the hospital. So determine the exponential function with initial value 12, increasing at a rate of 8% per year. You ready for this? Initial value, what goes up front, so this is p equals 12. And the growth rate, that 8% growth, we're going to find out, I think it says that, right? Increasing. It didn't say the word growth, it said increasing. That means we're going to do 1 plus, and I'm not going to put 8 in there, right? 0.08. And to the t. Dun, da, da, da. So there's your growth rates, increasing per year at 8%. So this is actually what we call the yearly growth model, or the per unit of time, 1 unit of time. So this one's the kind of the simple version of exponential growth. We don't have to worry about breaking it up into monthly and semi-annually and those types of things that might sound familiar to you. We'll get there, I promise. Oh man, poor Graham. Do you need something to play with? Where's your other spoon? I'm going to hand him another spoon.
I just wanted to peek at it.
Okay, we're back in action. Had a little pause there. But this increasing function, there it is, increasing at 8%, initial value of 12, perfect setup. So let's talk about mold, bacteria, things that, of course, come up when you're in a hospital stay. But you're at an initial value of 100 bacteria, so you put 100 bacteria in a petri dish, and then it doubles every hour. So when it tells you every hour, that's kind of an establishing of what the unit of time t is going to be. So t is going to be in hours, and it says it doubles. Well, how do you do double? That means it takes, and you're not adding 50%, that's half. If you're adding 75%, that's 3/4. You're adding a full 100% on top of what you already have. Doubling means adding another 100%, adding another of yourself for the whole initial amount. So it's 1 plus 1.0. That's what doubling is, adding 100% to the t. Well, we don't write, of course, that. We could simplify that, and it looks like 100 times 2 to the t. And that's our doubling function. So in general, when you're asking how long it takes when things are doubling so often, you can actually do 2 to the t. But I like to remind you it's just 1 plus 100%. That's the rate of doubling. We want to know when it gets to 350,000. This is a little algebra problem. It involves logs, because that t is what we want to solve for, and it's in the exponent. We need to get it out of there. So here goes. Hi, Granny. And so we're going to end up taking the log of both sides of this after we do just a little bit of work. We got to divide by 100 first. Get rid of that. So 100 out of there. Out of here, 100. I know, dude. I know. He loves logs. He just hates it when I do logs without him. So hang in there, Grandma. I'll let you do this next one, I promise. So there he is, 350,000, or 3,500. And then here comes the log. When you have that t out there, log both sides. It'll get it out of there. So we log. This allows me to pull the t out front. So now it's t ln2 equals the log 3,500. This is all in your calculator. Remember, ln is a button on there. It's above. Look for e to the x and log. They'll be together. Yeah, hold on, sweetheart. I'm almost there. And this is the moment of truth. These are numbers, remember. This is just a number, and that's a number. So if I want to get rid of it, I divide by it on both sides. Natural log here, divide by it, because it's multiplied to my t. So divide both sides by natural log. We've got ourselves a number. So I got my calculator out, just like you would. And yes, I hear you. Yeah, we're going to quit that one, clear. Natural log of 3,500. We're going to divide that by the natural log of 2. 11.77 roughly hours. There you go. Hours. There you go. But that's the story on those. Nothing too serious. But having to remember that there's a time when you have to solve for how long it takes to get to a certain amount. You will have to do logs. And it usually starts with divide out the constant, the initial amount. Then you can take the log of both sides so you can get the t out front. And then it's another division step away from solving for the rest of it. Cool. Now let's go back to that last page. The number 4 is the last thing on there. We have a half-life of a certain radioactive substance. It's 20 days. And there are 5 grams present initially. Now this is a little bit different situation. So we have a time of days. And what we know is the half-life is set up a little bit different. That means how long until I have half. And if I have 5 grams present in the beginning, what I'm interested in is, so that would be like my initial amount. We'll deal with the parentheses here in a second. I want to know, when do I have 2.5? Okay, how long until I have 2.5? The result of this, and obviously that's a decay, because you're not going to be able to find the time when it'll be 1 gram. And the cool thing is, and then what's our rate? Like, we have to figure out, it takes 20 days to get to that. So if I'm doing 1 minus some rate to get that to happen, and then I start, and it takes 20 days for this to occur. Yeah. There it is. So in our time, find the time when there will be 1 gram of the substance remaining. This is kind of a multi-stepped problem. One of the things we have to find out is, if I just put in everything that I know, the half-life setup, and the 20 days it takes to get there, I'm going to be able to solve for R, but I have to get that R back into another equation to find out how long until I have 1. Baba, did you drop something over there? So we're going to make a new equation when this is all said and done, when we know what the rate is, and we're going to put in we're going to solve for time. So it's a 2-part problem that takes a little bit of time. I'm going to pause here and help Graham for a second, and then I'll get back to that. Okay, I think we can finish this off now. We got some Disney Junior in the background. Graham's getting sleepy, looking very cute in the corner. But here's the last part of it. I told you there's a kind of a two-part problem. So I start with 5 grams, and I want to know when I get to half. That's when I set it all equal to 2.5, and it said 20 days, so I put 20 for time. We're going to solve for r. So that, excuse me, the left-hand piece, if you divide both sides by 5, we're trying to isolate r. You get 1/2, 2.5 divided by 5. Now we want to get rid of that 20, and you may not remember this, but to get rid of a certain exponent, you just do the 1 over that exponent. So I need to raise this to both sides to the 1/20th, or you can think of the 20th root, both sides. Same idea, just different ways of writing it. So the 1/20th power of both sides, or the 20th root. I'm going to do the 20th root here, but down below I'm going to write it as the 20th power. That cancels the 20th power on the right, so we get 1/2 to the 1/20th on the left, and then just plain old 1 minus r on the right. So I canceled that 20th power. And then I need to get r by itself, and I'm going to do a two-stepper. I'm going to add r to the left, and then subtract the 1/2 to the 1/20th to get r by itself. And this is the end result of that. And then if I solve it out with my calculator, 1 minus 1/2 to the 1/20th, totally a calculator thing. You got to type it in. And you want to make sure your exponent 1/20th is in parentheses so that it comes out okay. So if you guys want to pause this, try it out, see if you can work it, that'd be great. Now we need to use that new r in the second part of the problem, which is, hey, I need to find out when I reach 1 gram, but now I have the decay rate, so we're good to go, the 0.034, and now we need to solve for t, and that means logs to get that out of the exponent perch up there. Now divide both sides by 5 first. Remember, get away that constant. 1 divided by 5 is 0.2. Log both sides, pull the t out front on the right, and now we just divide both sides by that log of 1 minus 0.34, and there's our t. Just divide those two with your calculator and you will get a time. I'm going to let you guys do that because Graham's getting squirmy, and you just take off. I'll send an assignment via Google Plus, what problems to do, and you guys go ahead and share that with Miss Johnson there so that you guys can do the work. You just kind of lead the way. Grab a book and take off with it. Take care, guys. See ya.